Okay. Well, it looks like everybody, well, almost everybody who's going to be here is here. All right. So, with today being the day that homework 1 is due, and a few people have turned it in already. Now, because this is a rather large assignment, and also because it's MATLAB, and most of you are getting used to that, I want to make sure I'm very clear about what I'm announcing here. So, on the good side, I will not be enforcing the late penalty for this assignment. Okay, so effectively that gives you some more time. But here's the bad part. Well, I mean, nothing new that's bad, but just the way it has been. Okay, because if we go to the class website where you see all of the assignments, just remember, if you're taking a little more time on the MATLAB one, these other ones are still here. So it's not an invitation to just slide and then keep sliding. So now the other this assignment is also the main reason I'm doing this. There's a lot of problems. There's 29 problems. Whereas if you look at the subsequent ones, okay, this one's going to be changed, but I just changed this one. There's like not many problems in each one. Like there's 8 here, 6 here, 8 here, and so forth. And that's going to be the norm from this point on. Okay. So don't pay attention to this one. It's changing. The other thing is I've decided to make each problem in homework 1 worth 4 points, which means there's a maximum of 116. But as I said last time, and I'm still sticking with this, every assignment will be graded out of 100. So you have a little leeway there. So in other words, if there are, so for example, suppose out of the 29 problems, there's 4 that you look at it and it's like, and then the other 25 you do perfectly, you get 100. So there's a couple in particular, like day and year or day of week, that are quite a pain. But I would still encourage you to at least attempt each one, see if you can at least get some partial credit. Because you might think, oh, I've done this perfectly, but then you get it back and you're like, no. All right. There's a question here.
So if we do like all 29 questions, we'll like 16 points in the bonus point?
Yeah, so you can get up to 16 bonus points. Yeah, I'm not gonna cut it off at 100. So yes, so you have that buffer in case you mess up something else later.
Mm-hmm.
But that's not an invitation. Is there another question?
Until when are you accepting the homework?
Sorry, what?
Until when are you accepting the homework?
Given what I said about the late penalty, it no longer matters. Because I'm not enforcing it anymore. Because now, as a rule for assignments in general, because this will apply later. So on the day it's due, which is always a Tuesday, it's any time that day. Or I mean, okay. Suppose you stay up during the night and you submit it at 2 a.m. They'll still be considered on time because it's obviously extension of a current day. So
Before you wake up.
yeah. Whatever I wake up to is on time. I do wake up early though.
How early are we talking?
6 a.m. usually.
I'll be up.
Even on weekends without an alarm.
5 o'clock.
Yeah, so actual adulthood is awful. Okay. Questions related to the assignment?
So like how we get so much homework, we gotta go out with the test, right?
What?
Do you read the syllabus?
No.
I remember that so long ago. My brain been frying this one. I don't think I remember.
There's midterm and a final, but keep it like I said. The later assignments. So every single assignment except for this MATLAB one does. While there are a lot of them, each one does not have many problems on them. So what I'm hoping is that it'll be less intense than this one. Although this one was also spread out over a long time because I spent 4 class periods on MATLAB. But
What do you want for your birthday?
what?
So what do you want for your birthday?
Oh, what? Stop.
Y'all have like the same. Y'all have the same birthday?
No, mine's on the 7th. This is on the 21st.
Yeah. Okay. Yeah. So if you look at so on here, this is the schedule, and we are still on this schedule. Okay, so a month from today, class will be about the review for the midterm exam, which will take place on the 22nd. So it's a ways off, and naturally there'll be a final. So that's a 400 level math class. Other questions relating in any way to the assignment?
I know there was some that wanted it a certain way, like using the I was going back and looking at it, using the colon operator.
Oh, right.
And then I know, like, when I was looking up, like, help and trying to find out how to do certain things,
Yeah.
I saw other things that could have been used.
Right.
And so, like, say it said the colon operator for this specific exploration.
Yeah.
But the next one wanted something that kind of involved the same thing, but doesn't necessarily require a colon operator. Would it be okay to use something else?
Well, when it comes to MATLAB things, I'm not going to grumble about because if you guys are going off on your own and learning MATLAB features, I'm not going to begrudge you using them. Like this question came up about another problem. Stop. Let's see. This had to do with. Okay, this problem right here. When it figures out the day within the year. It says use if statements in a number of days in each month to compute this value. Now, the reason I worded the problem that way is that at this point in the book, if statements have been covered, and for statements not yet. I mean that's something that immediately follows. So yes, when I was writing a problem way back, I had in mind, okay, you could use some admittedly cumbersome if statement, but this is the kind of problem that can be done using a loop. And I think what I'd probably do in a future edition of this book is move this problem down a little bit, to after 4 loops are covered, so that it can be done either way. So if you do this problem, which can be done using some kind of loop, whether a for loop or a while loop, that's going to be fine. So, now, as far as things that would lead to a loss of points, if there's a situation where the problem asks for something, and now I don't mind if you're going to deliver that something in a different way. But if you don't deliver it at all, of course that's going to be a problem. Like if part of a question is just blown off, if that's something that will result in a loss of points. Yes.
Is that like on the question that asks about it, concatenating horizontally or vertically? If you don't answer in like the in the command window, like type out whether or not it was supposed to, if it did or did not, would that give us like lost points?
Well,
it did specify in the question it asked like I can't remember exactly what it asked, but it did ask about that in particular, not from being like.
Okay. Well, yeah, you do need to answer the question.
Answer all the questions.
Yeah. Now, I don't care if you want to do it as a comment in the command window or in a separate file. I mean, yes, I am getting a lot of questions about, the format of the homework being submitted. Okay, so number one, a lot of these situations, I genuinely don't care. Okay, so I want to dispel some things right off the bat, because I know that as a member of a subspecies of professors, there are certain stereotypes attached to me. Number one, I do my best not to be anal retentive. And I apologize if that language offends anybody, but I think it gets the point across. Yes, I'm aware of. I've had colleagues, past or present, and I'm sure future as well, who do something like they require that if you're turning in written homework, you must number the pages, 1 out of 1, or 1 out of 10, 2 out of 10, etc. And if you don't do that, they'll take off points. I don't care. So, I mean, I'm looking for certain content as specified in the question, and when I'm deciding whether to take off points or not, my guide is going to be, I'm going to look at what the question says. It doesn't matter whether it's a question of my own devising or from another source, and because that's what you're going on, so that's what I'm going to go by too. And the other thing is, yes, there's quite a bit of work, but that's kind of a mandate that's given to me. I do my best to not be a sadist, as faculty members go, and that's why, when the coursework gets difficult, I am here to help. Some of you have taken advantage of that, and some of you have not. And if you have not, and you're still having difficulty, then I encourage you to rethink that. Whether it's asking questions in class, or after class, or since shooting me an email, or whatever, I'm here to help you get through this. But by the time you get to this level, whether it's numerical analysis, modern algebra, real analysis, it's yes, the subject matter is going to be pretty intense, and that's what. But one of the things that's often tempting is, especially as it's over teaching the same class over several years, is to kind of water it down some, and that's when things go really badly. So, okay, so I just wanted to put that out there because I think just because of the nature of my position, there's sort of implicit assumption that I'm out to make you guys' lives miserable, and I know that they already are. So, okay. Any other questions relating to the assignment? Yes.
1 to 17.
17.
On some of the
Okay.
subdiagonal entries are not exactly 0.
Yeah.
Is that going to have to do with the code in your program, or is that going to be to do more with like round-off error and things like that?
The latter. Now, okay. Now the thing is, this question 1.2.17 is really. I'm doing this because just to get you guys to think about it, because the actual answer deals with material that is upcoming, but I put the question in there because when you're running this Gauss-Lim script and seeing what the matrix looks like, and you know what the matrix is supposed to look like at the end, you know it's supposed to be upper triangular, you know that those entries below the diagonal are supposed to be 0, and what I'm hoping, without me calling attention to it, that if you just went ahead and do that and see the matrix, like you saw it on my screen when I was doing it in a tutorial, that you would make that observation. oh, here's some values that are printed to be simply a 0, and then others that are not, like 0.0000, or even stranger, minus 0.000. And ideally, that should spark a little bit of curiosity as to, well, why would it do that? Why does MATLAB have 3 different ways of displaying what should be 0? So it's really just to give you something to chew on. But yeah, it is something I will get into detail a little later. In other words, I'm not going to be picky about grading it unless you leave it blank.
Also, 22.
22.
So instead of sine d, I was just saying sine degree. But am I supposed to set sine degree equal to a statement
Okay.
that involves sine?
Oh, okay. So your function, whatever you choose to call it. No, I would not recommend calling it sine d or cosine d because those names are taken.
It's a sine degree.
Yes, you called it. You spelled out degree.
Right.
Okay. Good. So, so your sine degree function needs to call sine.
So what I was trying to do was do something on the lines of sine, but I was trying to do times 180 over pi.
Yeah.
To make it become degree, but it's just not working out.
Oh, like you're not getting the right value or something, or not getting what you expect. Okay. So in other words, you're taking. So the input argument coming in is interpreted as degrees, and then you're converting to radians, right? And then passing that to sine. Is that what you're doing, or?
No,
Okay.
I was trying to set sine degree because I want it to be in degrees, right?
Okay. Well, the output value is just going to be whatever sine or cosine will be. It's just that since the input is interpreted as degrees, but sine and cosine expect radians, then you have to. And I mean, you mentioned you were doing some sort of conversion.
Right.
And that's applied to the input.
Okay.
Yeah. Whereas whatever you get from sine or cosine, that's the value. Yeah. Yeah. So yeah, that was the issue of like conversion to wrong place or.
So I should have done power 180 instead.
Yeah. Okay.
All right. Thank you.
Yep. Other homework related questions. As a reminder, I haven't had occasion to use this very much yet, but I mean, it depends on your emails. I'll check and see if I have any more. So these are the email questions that I've gotten to this point that I've considered were of general interest. And as I get them, I anonymize them and post them. Okay. Anything more about the homework? Okay. All right.
Question. Problem 25.
Oh, sorry. Which?
Problem 25.
25?
Yeah.
Okay.
So when you say it must plot any real root of the
I'm sorry. I cannot hear you. I need you to speak up, please.
Okay. When you say that the function must plot any real root of the polynomial in that interval, I don't understand what that means.
Okay. Yeah. Now. Okay. So one of the polynomial functions that I talked about. So use that to get the roots. But then you would be going through that list of roots to determine which ones of those are real valued.
Yeah. You said we should use the match function.
Oh yeah, because okay, I'll give you an example involving polynomial roots. So I'm just going to make a polynomial. Let's see. Okay, this is a randomly generated cubic polynomial, and I hope it does not have real roots. We'll have to do it again. Okay, so this one has some complex roots. So, because you want to know whether the imaginary part is 0 or at least very small. So if I do imag of r, that gives me the imaginary parts. So in this case, since this one has an imaginary part of 0, that would be considered, so that'd be a real root. So this is just a way to help you examine the imaginary parts.
No, I know how to examine.
Okay, but I'm not sure what your question is.
So when you say plot the root, because we are plotting the graph of the polynomial, right?
Yeah.
So when you say plot the roots in that same graph, what does that mean?
Yeah. Okay. So for instance, whatever real roots you get. Okay. All right. So plotting real roots on the x-axis. So these real parts would serve as your x values. So for instance.
So the y value becomes 0.
Yeah. That's what I mean by plotting on the x-axis. So that since that's y equals 0, so you've been plotting. So suppose you have 4 real roots. So you'd have a vector of 4 x values, which would be the 4 real roots, and then a vector of 4 zeros. And using red circles. So that way, on the actual graph, what you should see is where your red circles are, the polynomials should be passing through them. Yeah, when you mentioned imag, I thought that's the part you were asking about. So, okay. All right. Any other questions? All right. Okay. Let's see. All right. Now, for the first time, we are getting beyond, whoops. I need to change the scrolling here. Okay. All right. So we're getting beyond the MATLAB tutorial finally, already a few weeks in. Now, one thing I want to point out, so this applies starting from homework 2. Now, if you look at the assignments, okay. So for homework 2, I know you guys are, most of you are still finishing up homework 1, but hopefully by the time we get to Thursday, you'll have at least taken a look at homework 2, since I'm starting to cover this material during the rest of today. So what we have here is we have, again, some problems from the book, explorations, not as many. And then the other part of it is this, a concept check questions, and those are in Canvas. So if I go to the Canvas site for this class, there's a Hattiesburg section, but then there's there's 3 sections. There's Hattiesburg undergrad, then Hattiesburg graduate student, and then U5 at the coast. But the same thing in every section. If you go down the left side and click on quizzes, then you'll see here the first quiz, and you'll see which assignment each quiz is associated with. So, what will happen is you'll go here, and so in this case, I'm going to preview the quiz. So the quiz consists of a single essay question, but it's actually, these questions are taken from the book, because the book has a concept check section in it. So basically, I've just taken those questions and pasted them in here. Looks like I had to fix the spacing a little bit. So you'll type your answers in here. Now, the idea is that by reading through the section, you should pretty much find the answers in there. Like a lot of these questions deal with definitions, things like that. Wow, there's a few typos, evidently. that I need to fix. I'll get on that. And okay. And then if you finish it before the due date and submit this part, then I can. That gives me an opportunity to look it over and let you know if you've gotten anything wrong, so that you can try again. But once the due date passes, then that option is taken away unless you tell me that you're actually planning to submit the assignment late. But then the usual late policy will apply. Okay, so this is part of the assignment.
So the quiz is different. It's just by each section here's a quiz, and we go cover.
Yeah, well, so really for each homework, except for this first one, yeah, so each homework assignment 2 through 10 has this quiz associated with it.
So we have to go do the MATLAB stuff and then leave after that and go and do this.
So there's 2 submissions that fall under that same assignment. So for homework 2, so for homework 2, your 100 points will come from this, and then the problems from a book. So here in the assignments page, it listed everything that belongs to that assignment. But the idea is that since the concept check questions from the ones that are in the Canvas quizzes are basically reading quizzes, so you're not really doing actual math in that part. That hopefully that would not take you very long. But I put this in there because what happens very often is that students have been giving problems where you're solving equations or writing code or things like that, that they can do those things to a certain extent anyway, and still seem to have very little understanding of the actual concepts of a course. Like if I were to ask for a definition, something that we've already covered and used, that students would still not know. And that means you don't really have any ability to work with these concepts, certainly not beyond the class. So that's why I put these in here to try to drill some of that essential knowledge of these basic facts about concepts, methods, etc.
Okay, how are we going to send the MATLAB work to you?
Well,
By email?
yeah, that's still every assignment. That part, whatever the explorations from a book, always by email.
So we just save and send you, and I do it in a live script. Is that okay?
Okay, I've never actually used the live script feature, but by all means, feel free. And the thing is, with the Canvas part, once you submit that in Canvas, then I get an email from Canvas saying you've submitted this, so then I can go look at it.
But I don't know of any other way. I thought that's what the live script was for. The command, we can save the command window and stuff.
Okay, I apologize. I myself have never actually needed the live script feature. So that's something I'm not in a position to really comment on. I'm saying if you want to use it, you may.
So you recommend everything to do in the command window? What you say?
Again, I am open to whichever you prefer. Please understand that. I'm not requiring that you do everything in the command window. If you want to use a live script, you may use a live script. Okay.
So, what do you prefer? Sorry, I'm zoned out because I got
Yeah, that's it's a wrinkle, but I wasn't expecting either.
I'm
And
sorry, I'm using LiveScript also, so I just don't know if I need to convert it, but I guess I don't.
I'll tell you what.
Okay.
Please go ahead and submit LiveScript because apparently you've chosen that you want to do that anyway, and then because then that'll satisfy my curiosity as to what it's like.
Okay, I'm so sorry for the non-context.
Okay. So I will. When it comes to these things, I will say one more time. I don't care. So, and maybe that flies in the face of what every single one of my faculty colleagues thinks, but it's true. To me, LiveScript is the annoying thing that pops up whenever I either type in 2% signs for comments, or if I get code from somebody else and they've done that. So then I change it so that dang yellow goes away. That's my experience with LiveScript. So in fact, I think it'd be cool if some of you use LiveScript because then I can check it out.
So, even like 1.2.1, like it told us to type in the help function, but like you can't see that really unless I was to use like a diary.
Right.
Do you want to see that? Because I don't know how to.
Okay. Let me pull up that problem. Okay. Wait, where's? Oh, okay. Yeah, that. That's not something I really needed you to submit.
Okay.
Um,
Awesome.
Yeah, because this is something where this is your very first time actually working with MATLAB's math functions, so I thought it might be a good idea for you to do that. Okay.
Thank you.
Yep.
So should we edit that part out?
Sorry, what?
Should we edit that part out?
Yeah. Less content for me to scroll through. Yeah. Now, and I should mention that what I've done on some occasions, whether it's this class or a different class, if I, at the point where I decide to make myself miserable and grade all your assignments, because I try to do it all in a batch, just to get some momentum going. I really do hate grading. It's the least favorite part of a job, but it's made me pretty fast at it. But I try to be generous about it also, even though I don't like the process. But when I'm going through your assignments, if I come across somebody's assignment and I see that something of significance is just missing, what I generally do is I shoot them an email and ask about it. Because what if it's something like, for example, suppose there are problems on paper, which later problems, some of them will be, and they just forgot to send me that page. Because that's something we can get cleared up. Because, if you did the work, I'm not going to be like, oh, you forgot that page, 0. I don't do that. So that's something to keep in mind too. That I'm looking for certain things. If something of significance is missing, that would cause, especially something that would cause a significant point loss. I'm going to check about it. All right. And I realize that it may be a bad influence to be that lax about deadlines, because someone might say, well, what about real life deadlines and so forth? And what I've found is that real life is actually more permissive about deadlines than they want you to believe. And that's, I've only come across one deadline that is enforced with absolute rigidity, and that is with severe consequences attached, and that's the deadline for submitting an NSF proposal. So it seems like just about anything else I've encountered in whatever sphere of life, you talk to the right person, you explain the situation. Now, there are exceptions, but yeah. Okay. So I try to be reasonable. Okay. So, I don't know if I'm going to get to any new material tonight. That actually was the plan. But also, it's important to take questions about the homework also. And I also have Thursday. Now, as far as Chapter 2 is concerned, so actually, there's going to be not much MATLAB in this homework. This is all about error analysis, and actually, I haven't done this since the first day of class, where I type up these notes about the material. Okay. All right. So now the thing is, this section, there's a fair amount of discussion in here, in this section of a book. There's like 14 pages or so. Definitely more than I could go through every single detail of in just even two full class periods. So I want to point out, as I go through these sections, what I'm going to do here in class is go through the main ideas, and then, as time permits, examples illustrating those ideas. So that way, you have an idea of what's fresh in your mind and what to look closely at when you get to the assignments. And of course, class time is always to be used for questions on the homework too. Okay. All right. So if I go here, so my goal here is I've pre-made this outline. So these notes that I have, this is the section. So I'm going to make these files for every week because not every class period, but every week. So I'll be filling this in today and Thursday. So error analysis is the section that I'll be covering. So whatever sections I'm covering each week, I'll list up here. So this is section 2.1 in the text. And I filled in an outline of the main topic areas. So that's my starting point. And what I will do during today and Thursday is going through and filling this out with the essential concepts. All right. So first, as a introductory note, okay, it's acting funny for spacing. Oh, all right, I'm typing in the wrong place. I remember I typed down here, and it will show up here, including all the math. Okay. All right. Now, so some have said that as a definition of numerical analysis, is that it's nothing more than the study of errors. And on the one hand, that makes sense. Just because understanding errors in computation certainly is a huge part of numerical analysis. I personally would not go so far as to say it's the whole thing. Well, some books have made that claim. Because what are we trying to do? What is numerical analysis all about? So this is could be considered a valid definition because the goal is to produce approximate solutions. Hold on. And understand how accurate these approximations are. So certainly we need to have a solid understanding of the error that is produced when we try to compute a solution that's only an approximation to some exact one, but this isn't everything. So errors are about 2 of the 3 criteria for numerical algorithms. Because I mentioned this is back from first day, I know that was a while ago, so I will refresh your memory. So accuracy, of course, and robustness, which I never like the word robustness that much. Alternative word would be reliability. So how reliable is a solution? If you're running algorithm for many different inputs, you don't want something that works well for certain ones and fails miserably on others, because you put that in mathematical software and I guarantee you no one will want to use your software because they can't trust the answers. But what about efficiency? Numerical algorithms are supposed to be efficient also. And some of those considerations don't really deal with error quite as much. Some do, because what if you make an improvement to an algorithm's efficiency, but as a result it is less accurate? And yes, sadly, I've done that from time to time, and it's awful. Certainly, error is a big part of numerical analysis, and that's why I'm actually covering it first, before we get into anything else, because concepts that are covered in this chapter, Chapter 2 on error analysis, are going to pop up again throughout the semester. Okay. So what I'm going to do first is discuss the different types of error, because one of the insidious things about numerical methods is error could pop up all over the place. Given any numerical method for solving whatever problem, like a system of linear equations or an ordinary differential equation, there's going to be literally zillions, and yes, I said literally zillions, of opportunities for errors to be incurred. Because algorithms these days perform millions or billions or trillions of computations. Each one of them can be erroneous. So where can error actually come from? So there are 2 broad types of error. So first is data error, and what I mean by that is error in the original inputs of a problem. And as opposed to computational error, error in the process of obtaining the output. So already what I'm typing here is going to get poised to get a little cumbersome. Going to talk about error in input, error in output. So I'd like to be able to refer to these things more concisely. So any algorithm can be described as computing simply y equals f of x. Now, we have to be very general about this. I'm not talking about just a function of a single variable. X can be a number, it can be a vector or matrix, or it could be a collection of parameters. So X is very broadly defined here. So it's whatever input you have to the problem, if that is erroneous, that would be data error. Now, the best example of data error, measurement error. The input to your algorithm can be is likely obtained by some sort of measurement. Measurements are erroneous. Like, ever since you were in elementary school using a ruler that had accuracy to 1/16 of an inch. So That gives you an idea as to the limits of a precision of that instrument right there. Or any instrument, no matter how rudimentary or sophisticated, there's going to be some limit to the accuracy of the X that's coming into the problem. Bless you. Okay. And then computational error is once that X, whether it's exact or erroneous, is plugged into your function f. So f. So the process of obtaining output is mathematically it's the evaluation of. Oh, I hate when this happens. Okay. The evaluation of f at x. So x is the input, y is the output. And then f you can think of as the algorithm for computing y. Now, you're accustomed to very simple algorithms f, like mathematical functions, sine, cosine, square root, etc. Although some of those functions I just named, the actual algorithm for computing those, for real, like within MATLAB, is not so simple. Something like trigonometric functions or exponential functions like that, or even square root. Basically, anything that's not a polynomial or rational function, the process to evaluate those functions is quite complicated. But f can be something very elaborate. For example, suppose x consists of a matrix and right-hand side vector, and the output is a solution of a system of linear equations described by that matrix and vector. F is the algorithm used to obtain the solution, which could be Gaussian elimination and substitution. So that'd be an example of an algorithm F. But for discussion in this section, we're not going to get into the details of what F might be, but just talking about algorithms in general. Okay. Now, so the thing is, so for notation purposes, I'm not sure why that question mark is showing up there. Thing is, I remember I last used this program, well, besides the first day of class, also 2 years ago when I last taught this class. And I remember being aggravated by certain aspects of it, certain bugs, and now I remember what they are. Okay, so I'm going to use hat x is the approximate input, hat y is the approximate output, hat f, stop that, approximate algorithm. So anytime you see a quantity with a hat on it, at least in this chapter, it's referring to the approximation. So then the unhatted quantities are the exact values, which are often either unknown or unattainable. Okay. So for instance, if we have a x that is not exact because it came from measurement, really x hat is the input. Okay. Now within computational error, there are a few of those that I'll go over real quick. So we have what's called discretization error. I'll list them first, and then I'll go over them. Truncation error. And finally, round-off error. Okay. So discretization error is... sorry. Okay. So what happens is continuous quantities placed by discrete approximations. And it's best that I give an example for that. If we take f prime of x, the derivative of a function, and how is that defined? It's a limit the limit as h goes to 0 of difference of two function values divided by h. Okay. So this is the exact quantity. So this would be some function of x. But we're also taking the limit as h goes to 0. So h is getting arbitrarily close to 0 and never actually reaching it. So this can be approximated by f of x plus h minus f of x over h for h very small. Okay. So if I choose h to be small, this should give me a nice approximation of a derivative, but it's not the same as letting h go all the way to 0. That would give me the exact value. So this is an example of discretization error, where I'm choosing some non-zero fixed spacing h to find the approximation of this derivative. Another example, replacing an integral by a Riemann sum. An integral defined as the limit of a Riemann sum as the number of terms goes, or like that represent rectangles, goes to infinity. Well, we can't go to infinity. We got to stop somewhere. So we, so replacing limits by quantities where we're getting close to that limit, but not quite at it, is an example of discretization. Okay. All right. And we'll see more concrete examples of these later in this section. Okay, truncation error. So examples of this would be, so many algorithms are iterative, meaning the exact value obtained after infinitely many iterations. And an example of this came up in the homework. Newton's square root. So I had a while loop that would perform an iteration that would convert to the square root of 2. And in the code, it stopped after 5 iterations because it was within, it had the square root of 2 accurate to about 15 decimal places. But the point is, the exact square root of 2 would require letting that iteration continue to infinity, which we cannot do. So we take but in other words, all these infinite processes of various kinds stop somewhere. Another example that we'll get to more later: Taylor series. Taylor polynomials are an important part of numerical analysis. In fact, one of my professors from my undergrad days at Purdue, different black and gold school, actually referred to Taylor's theorem as the fundamental theorem of numerical analysis. And actually, I'd kind of have to agree. Okay. Wait, something is... Okay. All right. So for functions that you would have seen these in like Cal 3, for instance. And this is my gripe about this program, like e to the x, sine x, etc. So you learn Taylor series for these. We'll see them again. So it's okay if you forgot. So as the number of terms goes to infinity, you would get exactly these functions. So we're going to cut that off after a certain point, and also have an understanding of how much error is occurred as a result of that. But yeah, so that's a source of error that we have to try to measure. And then finally, round-off error. So error in arithmetic operations due to limited storage for numbers. Because take transcendental numbers or irrational numbers like e or pi that have infinitely long decimal expansions. Well, we can't handle that. A computer can't handle that. So we have a certain amount of fixed storage set aside. Now, there are software packages that deal with what's called variable precision arithmetic that will adjust the precision to accommodate more decimal places. And generally, that's not used in many applications just because that is arithmetic done in software rather than hardware. Therefore, it's extremely slow. So that's why in this class, we're dealing only with a finite fixed amount of precision. Okay. So these are the three types of computational error. So in this process of computing y equals f of x, by really computing y hat equals f hat of x hat, a lot of different things can go wrong. And so one of the important ideas is how does error grow when performing algorithms? Can error that's coming in be amplified possibly? Because that's a serious concern. All right, now, okay, so in this chapter we're going to be examining and see examples of this kind of error, and we're going to spend actually it's next week is when we'll get into round-off error in particular. So prior to that, we'll be dealing with these. Okay, now another thing I want to mention is that ideally problems should, whatever problems we're trying to solve, should be well posed. A term that's often ascribed to PDEs, partial differential equations, but really applies to other problems too. So there are three conditions for well posedness. 1, the solution exists. 2, solution is unique. And 3, and this one is particularly important for numerical analysis, as a solution depends continuously on the data. So whatever input there is to the problem, for example, like in system linear equations, the data would be the matrix or the right-hand side. Now this is how this third condition is always written. But I don't think it's very intuitive, so I'm going to give my own translation into English. Small change in the data should not lead to a large change in the solution. So again, like back to the example of a system of linear equations, or maybe a differential equation. You have initial conditions. What if the initial condition or coefficients changed a tiny bit, like on the order of 10 to the minus 5 or whatever? Then if a solution was thrown off to a large degree, that's really the kiss of death for numerical analysis. Why? Because there's always going to be error. Problem data is always going to be off. You just have to go in with that assumption. So that means that when a problem has this kind of situation where it can be thrown off by a lot, then we have to rethink. And maybe there's something about the problem itself that can be adjusted. Because when a problem is ill-posed problem, that's in other words a problem that is not well posed, they cannot be solved numerically by any method. Because for certain problems, like derivatives and integrals, we're going to learn multiple methods for solving them, and there's rarely a clear-cut case of one method being the best, even though their creators will try to claim it is. It's a lie. That problems may be, certain methods may be the best one for certain situations and maybe practically the worst in others. But at least in those cases, the problems are well posed. But it's ill posed, you can try all different methods and can't really be assured of having an accurate solution. So we try to steer clear of that. Unfortunately, we can't entirely. Some problems really are going to be bad. Okay. So we just try to contain that a bit. Okay. Now, how do we measure error in the first place? So to get some basics down here, really this is more about terminology than anything else. There's absolute error and relative error. Okay. Now, so the idea is absolute error is just the difference. Whoops. Get me in math mode, dang it. That's so aggravating. Sorry. I'm going to grumble about this all semester long. So absolute error is nothing more than just plain old difference, subtraction, between, so it's the approximate value minus the exact. And then relative error is the same, except for relative, what makes it relative is we divide by the exact value under the assumption that it's non-zero. So obviously, of course, it cannot be used. So
can the absolute error be positive or negative?
yes. So error is signed. Some books might define absolute relative error using absolute value. Here I don't. I would try to be more flexible because sometimes the sign of the error actually is of interest. Most of the time, not. And usually it's a matter of just how large it is. Okay. Now I'm going to give an example of certain computation. So okay. So let's suppose that the exact value y is equal to 1, and then, well, actually, I'm going to make it a larger number. Y is equal to 100. And y hat, approximate, is equal to 100.1. Actually, I'll make it my first example. And then my second example, y is equal to 0.5. And then my approximation is 0.6. Now, intuitively, what approximation feels to you like it's the more accurate one? Yeah, why is that? Why do you think that? I would agree, but
It's just, I don't think I'd put it in words because you're in a larger amount. So, yeah, the percentage.
okay, percentage difference.
Yeah.
So, which notion of error does that deal with? Relative error. Yeah. So we
They both have the same absolute error.
Right?
sorry, what?
Saying it's smaller would be more accurate.
Wait, small. What is smaller? Like,
I'm saying if it is smaller, then
Um,
it should be more accurate.
right. But so the thing is,
They have the same absolute error.
Yes.
But whenever you put in the relative error by dividing, you get the percentage.
the absolute error is the same, but the first relative error is much smaller. And what we were doing instinctively is focusing on relative error. And formally, and really, relative error is percentage error. It's a number. You think of it as equivalent definition. Okay. Okay. Now, and actually, yeah, so actually I contrived this example so that the absolute error in them would be the same. It says 0.1 in both cases. But yeah, here, this one is, it's a 20% error. But so now I'm going to have another example. Wait, actually I'm going to send us to a new page. Okay. So consider this example. The exact value is 10 to the minus 8th. And then the approximation is 1.1 times 10 to the minus 8. Actually, I'm going to make that a 2. 1, 2. Okay. Now, you play a game like, one of these things is like the other, not like the other. So now I want to mention I have the same number of zeros in front in both cases. So here we have 10 to the minus 8 over here, and then 1.2 times 10 to the minus 8 over here. So this result, this approximation, is equally accurate to one of these in one of these senses, absolute or relative. Which one?
Relative.
Yeah, this has the same relative error as which of the previous two examples?
As the first example.
Wait, for this one?
Yeah, but wasn't the relative error on the second one 0.2?
Yes.
So the first one didn't have the same relative error as the first one? No.
Well, wait.
Oh, no, it's the second one.
Yeah, these are, so this example is contrived to have the same relative error as this one, 20%. That's actually why I changed the 1 to a 2, to make it the same. So in this case, this is, so this has a rather large relative error, tiny absolute error. Okay. Now, so for all three of these, which really is the notion of error that is do you think is most informative about how accurate each approximation is?
But out of absolute relative?
Yeah.
I think relative would be much better.
Always?
No.
When might it be not as informative?
You're not looking at in comparison to other errors, or
Yeah, or in other words, when might absolute be preferable to relative? Is there a situation where that might be the case?
Do it smaller.
What?
You do it smaller.
Yeah, because, well, for one thing, relative error cannot be used if y is 0. If y is near 0, so absolute error recommended if y is near 0. And because what can often happen is whatever errors you may be getting are likely rounding errors, especially since we have limited precision anyway. Like if you have some values where the exact value is like on the order of 10 to the minus 15th, and your approximation is also on the order of 10 to the minus 15th, and maybe the second non-zero decimal place is off, that actually would lead to a large relative error. But because the values involved are so small, now small may mean different things in different applications. So this is not a blanket statement, but sort of conventional wisdom. That a lot of times a low relative error in such cases may simply be unattainable. If I do a more extreme example, like this, like suppose your y value, exact value, is on the order of 1 billion. Let's say the exact value is 1 billion. And then the approximation is 1,000,000,001. I think in some cases, an absolute error of 1 would be horrible, but not in that case. So, go to the other extreme, relative error is definitely what you want for that. And if the values are around 1, well, then they're about the same. So there's sort of a spectrum here of whether relative or absolute error is best. Okay. Okay. I got 15 minutes. Okay. Now, so building on these definitions, absolute and relative error, I'm going to go to 2 other notions of error that are related, forward and backward error. So, and now we come back to a process of computing, of approximating y equals f of x, which is exact input, exact algorithm that produces exact output. That's what we'd love to have, but we generally can't. So we're approximating by y hat equals hat f of, and for sake of discussion here, I'm going to at least assume we're going to focus on computational error. So I'm going to let x be exact in this case. And in some cases it might be. Like, what if the input to your problem is 1? It's not derived from a measurement. It's just the exact value. We have forward error. Now, for each type of error, forward and backward, then we have absolute and relative. So we have, it's the error in y. Okay, so that would be so for instance, for absolute forward error, these same definitions from before, except the difference is now they're being applied to specifically to the output. In other words, we have an interpretation of y now as the output of an algorithm. Whereas, and this is what we care about, because that is obviously what we want to be truly accurate. Of course, we want to have accurate input, but it's accurate output that's the bottom line for us. Okay. Now, backward error, that is the error in your input, error in x. So that has the same definition for absolute and relative. Okay. So this is error that is relatively easy to get a handle on. For example, suppose x does come from some measurement. Then we could at least get an upper bound on this error. Like, for example, again, a rudimentary case of a ruler that has 1/16 inch accuracy. So you take your measurement, and you can say it's safe to assume that the absolute error in your measurement is in the interval plus or minus 1/16 of an inch. So you have lower and upper bounds on your backward error. But then suppose you take that measurement, that erroneous measurement, and use that in an algorithm. What's going to be done with that error? is that error going to be amplified? Is it going to be damped out? Either one can happen. So we really want to see if this is plugged into some algorithm, what this error is that's produced. But again, that's much harder to figure out. Unfortunately, it's also what we need. Okay, so we want to try to, if we can, we'd like to be able to use this error to try to estimate this error. Okay. Now, and this leads to what is called, okay. Backward error analysis. So what's done in backward error analysis is we assume the approximate solution is the exact solution of a nearby problem. And that sounds like a strange thing to say. So I'm going to cast it in mathematical terms. Meaning that my approximate output, which is f hat of x, is assumed to be equal to the true algorithm applied to some erroneous input. So in other words, I've shifted the hat from the algorithm to the input. So the reason why this is, typo here. Okay. So the reason why this is helpful sorry, my cursor is jumping all over the place. Okay. Okay. This is helpful because it takes f hat out of a picture. So if we can, so in other words, we're focusing on the actual problem that we're trying to solve. So if we can get some way of estimating the backward error, so in other words, if our approximate solution is the exact solution of a nearby problem, and we have some idea of how nearby it could be, then that will help us estimate the forward error, which is what we really want. Okay. So it allows us to focus on f itself, in other words, the exact algorithm, and we can, and the nice thing is about that is, depending on what f is, it lets us use derivatives. So calculus can help us with our error estimation. All right. So backward error analysis, you can think of it as a roundabout way to get what you're after. Forward error, it can be extremely difficult to estimate directly, but backward error is something that we can get a better handle on. So it's like a back door to the forward error. Now, suppose we can estimate backward error. We still need a way to get to forward error, and that's where conditioning comes into play. So if I were to give a very short definition of the condition number, of a function f, you can think of it as like your exact algorithm. But what I mentioned here is, actually, before I get into this, condition is about the underlying problem you're trying to solve. not the method used to solve it. Whereas stability, because notice this section is called conditioning stability. Stability is about the choice of algorithm. Okay, so one thing to be very careful about, and I had to watch my own words here, because you have some problem you're trying to solve, like examples I often use, system linear equations, differential equations, etc., or even something simpler like a derivative or an integral. That's your underlying problem, and you're trying to find an approximate solution of it. So it's important to pay attention to what are properties of your problem as opposed to your method. So we can have well-conditioned or ill-conditioned problems, which is related to well-posed or ill-posed. And we would have stable or unstable algorithms. Okay, so focusing on, I know I'm almost out of time. Okay, so what is a condition number? It's, if I were to give a very quick definition in words, all it is forward error divided by backward error. It's just a ratio of forward and backward error. Now the thing is, we already seen we have two types of forward and backward error. We have absolute and relative. So this means we have both absolute and relative condition numbers. So you have to be consistent. In other words, it's absolute forward error divided by absolute backward error is the absolute condition number. You can't mix absolute and relative errors. And I should say the default is relative. So in other words, if I simply say the condition number, that's generally interpreted to mean the relative one. So relative forward error divided by relative backward error. Okay. Now, the forward error is what we really want to get a handle on. And I've just mentioned that we don't have it. So you're thinking, how can we get the condition number? Well, I'm not really expecting you to. Or no one's really expected to. So the way error analysis works is if we can first bound the backward error, in other words, error in the input, and then the second thing is if we can estimate the condition number, get a handle on forward error. And I say get a handle on because, of course, you're never going to get error exactly. If you could get the error exactly, we'd have the exact solution. If we can get some sort of upper bound on the forward error, that is generally the best we can hope for. And what we'll see is that for some problems, we actually can do that. And that's good enough for our purposes. We want to have an idea of order of magnitude. So if we can have that's informative. In terms of comparing methods, is this method a good choice for this problem, or is the problem itself hopelessly flawed? That's really what we're after here. So that's how this process is going to go. So having some idea about the condition number is one of our stepping stones, and that's why backward error analysis is helpful, because by replacing f hat of x with f of x hat and being able to work solely with f, then we can estimate a condition number much more easily. And I'll show you how for the case of absolute condition number. So how do we get absolute condition number? That is simpler expressions, and I'm running out of time. Okay, I have 2 minutes. Absolute condition number. I'll make this last point, and then we'll be done. I'll use kappa. It was subscript ABS for absolute to refer to the Greek letter kappa. So it's a Greek K. is often used to refer to a condition number. So that is forward over backward error. So what is forward error? That's approximate y minus exact y, and then we have over difference of approximate x minus exact x. Okay. So if I work with this a little bit, okay, but what is y? Y is our exact output, that's f of x. And the approximate y is hat f of x. Now this expression right here, we can't really simplify that. But that's where backward error analysis comes into the picture. We're going to assume that this is the exact solution of a nearby problem. Now we can do something with this. Can anyone tell me what this expression, at least approximately, is equal to? Slope, which is so the slope of a function is its, which is we call the one word derivative. Yes. Yes. So really, I should have put absolute values in here. Well, I'll put stupid little absolute value signs here. Although how I would do it right would be using there's a way to size them. Okay. So really, for a condition number, we should be dealing with magnitudes of errors. Yeah, so that really is the absolute condition number. If it's a kind of algorithm and you can take a derivative of, which is not always the case, but for many important cases it is. So that is the absolute condition number. And then the relative condition number is derived in the book, but it's really x f prime over f is the relative condition number. So again, calculus really helps us here. So this gives an estimate condition number. So that times an estimate of backward error gives us an estimate of forward error. Okay, I know I'm out of time. It's 8:01. So I will continue with this on Thursday. And I'll post this along with the video. We should have a video tomorrow morning.
That PDF will be.
Yeah, that'll be posted. Yeah, all on the lectures page. Yeah.
Yeah, it'll be posted Thursday.
Oh, which thing?
Then you're gonna finish it on Thursday.
Or Wednesday.
I mean, no, I mean, but Thursday, we're gonna finish this chapter.
Oh, I'm sorry. Oh, yeah, I'll update it.
You
Yeah,
will update it.
yeah.
Okay.
I was like, I'm not coming back tomorrow.
Yeah.